We continue our exploration in Module 6 of how we can alter and modify different chemical equilibrium conditions by looking at buffer solutions. It turns out that this is actually a very natural way to move on from the titration curves that we talked about at the end of the last lesson to something that really is very practical and very important in our everyday lives. Our learning goals for this will be first to define what is a buffer solution, and then to talk a little bit about how a buffer regulates the pH of a solution, that is its main chemical activity that we find in use both in biological systems and in medicine. So let's review a little bit of what we learned about weak acid titration in the last lesson. First of all, if we start with a weak acid, in the beginning, all we have is the undissociated weak acid, and everything else is minor. As we add base to that solution, we enter a buffer region, and the things that are present in the buffer region are typically predominantly HA and A-. Remember that the hydroxide ion that you're adding is mostly converting HA, the undissociated weak acid, to its conjugate base, A-. So those are the main species that you find present in the solution at the buffer region. Once we get to the equivalence point, we've now eliminated all of the weak acid, the undissociated weak acid, from the solution. So what we have at that point is essentially just the conjugate base and a residual amount of hydroxide ion and hydronium ion that come from water autoionization. But because the main thing that's in there is the conjugate base, that makes the pH at the equivalence point slightly above the neutral pH. Okay, it is a basic solution. Once we go beyond the equivalence point, we still have that conjugate base, A-, in the solution, but we also have an increasing amount of hydroxide ion, and that's really what dominates the pH in that stage of the titration curve. When we're in the buffer region, as you may recall from the last lesson, the predominant equilibrium at present there is the equilibrium of hydroxide ion reacting with the undissociated weak acid, OH- plus HA, forming the conjugate base, A-, and water. And as we mentioned last time, that equilibrium constant is actually very large. It goes essentially to completion, not all the way to completion, but essentially to completion. When we reach the halfway point, that's the point at which we've added as much hydroxide ion as half of the amount of the weak acid that's there. So we've basically taken half of the weak acid and we've turned it into its conjugate base. So what that means is that when we're halfway to the equivalence point, we have roughly equal concentrations of HA and of A-. At this point, in order to understand quantitatively what's going on in the solution, it's useful to give you some insight into the Henderson-Hasselbalch equation. Now, I'm not going to go into a detailed derivation. I don't know that you're really interested in following a few math specs, even though they're fairly simple mathematic steps that you need to take. All right, but essentially it comes from starting with the expression for the weak acid dissociation, which is given on the left-hand side. Ka is equal to the hydronium ion times the A- concentration divided by the undissociated weak acid concentration. Now, if we were to take that equation and take the logarithm of both sides, all right, take the logarithm of the Ka, we get something that is like the pKa if we then multiply it by a minus sign, and that's step 2. So we can turn Ka into pKa by taking the negative log of that side. If we take the negative log of the right-hand side, we're going to end up with a negative log of that particular expression involving different concentrations in the solution. If we rearrange that expression, then what we'll end up with is an equation that relates the pH of the solution to the pKa. And so this is a situation where pH is equal to pKa plus the log of the ratio of A- to HA concentration in the solution. So let's think a little bit about what this means. If we had a solution that contained all of these different quantities, we could basically find the pH quite easily just by knowing the concentrations of A- and HA and also the pKa of the weak acid. So if we have all of those things, this gives us a way to directly calculate the pH without solving an equilibrium problem or whatever. I should mention that the Henderson-Hasselbalch equation is not for solving equilibrium problems. You can't actually find this point, but if you are in a solution that has known values for these concentrations, you can use that to determine what the pH is. Now, a special point occurs when the two concentrations, the A minus and the HA concentration, are equal. Okay, when that happens, think about what happens in that equation. We have pH is equal to pKa plus log of the ratio of two quantities that are equal, so that's the log of 1. But the log of 1 is just 0. So at that particular point, we find that the pH is directly equal to the pKa. All right, this is part of the beauty of the Henderson-Hasselbalch equation, because what we're going to be interested in doing is creating solutions that have a particular pH, and this gives us a handy tool that we can use to design those kinds of solutions. Those are buffer solutions. Now, strictly speaking, a buffer solution is a solution that is resistant to change in pH. Oftentimes, it is resistant to change, and it also features nearly identical concentrations of the weak acid and its conjugate base in the same solution. So if we consider something like acetic acid, if we're making a buffer with acetic acid and the two concentrations are equal, HA is equal to A minus, and they're both equal to 0.2 molar, then what the Henderson-Hasselbalch equation tells us is that the pH is going to be, again, the pKa plus log of 0.2 divided by 0.2, which means it's just equal to the pKa, and for acetic acid, that is 4.74. So we've actually very quickly, just knowing the pKa, we've gotten to the pH of this solution that contains acetic acid and acetate ions in equal amounts. Now, you might ask, what happens if those two quantities are not present in equal amounts? What if I have 0.25 molar of HA and I have 0.5 molar of A minus? So this may be where I take some acetic acid and I mix it in a solution to make it 0.25 molar in the acetic acid, and then I add some sodium acetate into the solution. So I'm adding A minus without adding any more acetic acid. And I add enough sodium acetate to that solution to make a 0.5 molar solution. That's how I might create this. Well, at that point, the Henderson-Hasselbalch equation would tell us that the pH is equal to the pKa plus the log of 0.5 divided by 0.25. Remember, it's always going to be the A minus divided by the HA. In this case, that then becomes 2. So we have pKa plus log of 2. And in base 10, log of 2 is 0.301. So pKa plus 0.301 is 5.04. So we can see that what has happened by altering this ratio of HA and A minus is that we've changed the pH from the 4.74 when they were both equal to 5.04 when the A minus is in double the concentration of the HA. So this gives us a prescription for finding the pH of a buffer solution. We're going to first find the pKa of the weak acid. We're going to compute the ratio of the two concentrations that are the conjugate base and the undissociated weak acid. And we're going to compute the logarithm base 10 of that ratio and add it to pKa, and that will give us the pH. So it's a very simple prescription, and one that I hope that you can implement quite readily on your calculator. How would we design a buffer solution? Well, first of all, usually when you're making a buffer solution, you're interested in creating a buffer that is stabilizing a particular pH. So let's say, just for the sake of argument, that what we're trying to do is to create a buffer with a pH of 4.5. All right, and we look in a pKa table of acids, and we find there's no acid there that has exactly 4.5. Okay, if there were, that would be ideal. But we have 3 good candidates of acids that are weak acids that have pKa's in that neighborhood. Okay, and I've listed them here: propanoic acid, acetic acid, and benzoic acid. All right, ideally, when we make our buffer solution, for a variety of reasons, it is advantageous to make a solution that has those two concentrations of undissociated weak acid and its conjugate base as nearly equal as we can make them. Okay, if we do that, we're going to improve the performance of the buffer. We're going to improve its ability to maintain a certain pH. So what that also means, though, is that we're going to be looking for the weak acid that has a pKa closest to the pH that we desire it to have. So we're looking through these three weak acids, and we want to choose the one that is closest to 4.5. So if we compare all of them, what we would find is that, in fact, it's the acetic acid that is closest to 4.5. So it's the one that we should use to make this buffer solution. All right, the next step is that we need to find out what concentration ratio will enable us to achieve that pH of 4.5. So again, we use the Henderson-Hasselbalch equation, but now that ratio is something that is an unknown. So we're going to treat it as the variable that we need to find when we are making our buffer solution. We know the pH, it's 4.5. We know the pKa of the acid we're using, it's acetic acid, and so it's 4.74. So we end up with that first equation where we've got essentially 4.5 is equal to, and look at the far hand right side, is 4.74 plus the log of that concentration ratio. So now to solve this, what we want is the thing that is the argument of the logarithm. To solve this, we would subtract 4.74 from both sides, so we would get negative 0.24 is equal to the log of that concentration ratio. We can then solve for the concentration ratio by undoing the log. So we take the inverse log, and that's basically taking the number that's on the left-hand side of the equation and raising 10 to that power. So the concentration ratio is going to be 10 to the minus 0.24. We can plug that into our calculator, and the calculator should tell us that that gives us 0.575. So that's the ratio of the concentrations. So how would we use that in a practical way to make our buffer solution, the one that we want? Well, if, for example, we know how much acetic acid we have in the solution, and it's 0.4 molar, then what we really need to know is how much of the sodium acetate we need to add so that that ratio of acetate to acetic acid is 0.575. So that equation is drawn there. A minus divided by 0.4 is equal to 0.575. So we just multiply both sides by 0.4, and we would find that the concentration of acetate ion that we need is 0.230. So that's how much sodium acetate we would need to put in that solution, or that tells us something about the amount of sodium acetate we would need to put in order to create this desired buffer at this particular pH. Now, let's suppose for whatever reason we had chosen to use benzoic acid instead of acetic acid. You may recall that it had a pKa value of 4.19, so it's not quite as close to 4.5 as acetic acid, but it's still reasonably close. What we would have found is that the ratio of those concentrations would have been 10 to the 0.31 or 2.04. So in other words, we need twice as much twice as much sodium acetate as the acetic acid that we have in there. So if we figure out the concentration of acetate, it would be 2.04 times that. If we had the same amount of acetic acid, 0.4 molar, then that would end up being about 0.8 molar sodium acetate that we would need in order to create this particular buffer. So what are the general steps that we need to follow? The first is, obviously, you want to determine what you want the desired pH of the buffer to be. Okay, and it depends a lot on what purpose that you're going to use it for. For example, your blood is a buffer solution, and it's trying to keep your pH, the pH of your blood, around 7.4. So it does this using carbonic acid as its buffer material, and it has the concentrations that generally keep the blood at roughly a 7.4 pH. So once you have your desired pH, then you look for a weak acid that has a pKa value near that. Okay, that was acetic acid in the example that we worked through. Could be something else depending upon what the desired pH is. You then use the Henderson-Hasselbalch equation to find the ratio of A minus to HA. Once you have that ratio, that tells you what proportions you need to mix those two quantities in your final solution in order to get the buffer of the desired pH. So now let's see if we can understand how buffer solutions actually work. I want to contrast two scenarios, one in which we're adding 0.01 moles of nitric acid to pure water, and we'll say to a liter of pure water, which has a pH of 7, and then later we'll add that same amount of nitric acid to a buffer solution. So when we add the nitric acid to the water, the pH is simply going to be the minus log of the concentration of the hydronium ion, which is of course the 0.01 moles per liter. So it'll be minus log of 0.01, or we'll have a pH of 2. Now this is a pretty acidic pH, as we would expect, since nitric acid is a strong acid. Not the strongest pH, because you can certainly have pHs that are even negative, but it's still a pretty strong acid. All right, what's going on in that reaction is that essentially the nitric acid is entering the water. It's completely dissociating to form hydronium ions and nitrate ions. It's a complete reaction, and it generates a very large pH change from the original pH of 7 to a new pH of 2. Let's contrast that now with what happens in the acetic acid buffer solution that we have talked about prior to this. But we're going to choose the one where HA and A minus are equal to one another at 0.20 molar. All right, so we're going to be adding 0.01 moles to a liter of acetic acid buffer solution where the initial concentrations of HA and A minus are 0.2 molar. So it's fair to ask, what is the effect of the nitric acid in that solution? In other words, what happens? Well, the nitric acid is putting hydronium ion in the solution, and those hydronium ions are going to find those A minus ions, the conjugate base of the weak acid, and immediately protonate them to form undissociated weak acid and water. So in effect, adding acid to the buffer solution is converting some of the A minus into HA. So we're going to be depleting the A minus by a little bit and adding to the HA a little bit. Okay, now both of those are starting at 0.2 molar. So if I'm adding 0.01 moles in a liter of this, of nitric acid, I'm going to basically convert 0.01 molar of the acetate ions, the A minus ions, into HA ions. So the final concentrations of these two things, I'm going to have HA will now be 0.20 plus 0.01, and the A minus will be 0.20 minus 0.01. So what does that look like? Okay, if I draw up my Henderson-Hasselbalch equation, now my situation is this. The pH is going to be the pKa of the acetic acid plus the log, and now the new ratio is not 0.2 to 0.2, the new ratio is 0.19 to 0.21. And that's going to be pKa plus the log of 0.905, that's what that ratio gives you, which changes the pH to the pK of to 4.70. Sorry about the typo on the slide. It should just be equals 4.70. So what has the net effect been? Well, in the case of adding the nitric acid to the water, it changed the pH by 5 pH units. That's a big change. In the case of the acetic acid buffer solution, it changed the pH from 4.74 to 4.70. So it's only changed the pH by 0.04 units, a very small change. So that means that we have basically shielded that solution against large pH changes even when we add a strong acid. A general note on these kinds of processes is that the ratio of those two quantities, if it decreases, okay, basically what we've done, we've had to add acid to it to decrease it because we've converted some of the A minus into HA. That will cause the pH to decrease or to become more acidic. If, on the other hand, we have added base to that, the base has the opposite effect of adding acid. It converts HA into A minus. So that means that that ratio would increase, and it would cause the pH to increase or to become more basic. So hopefully all of this makes sense, and you can begin to develop some intuition for how these things affect the pH of the buffer solutions. Now, one question that you might naturally have is, what is the capacity of a buffer? Well, typically, it's going to vary by the buffer, but it's typically going to be greater the larger the concentrations of HA and A minus are. That's going to give you greater buffer capacity. Now, what do I mean by that? But greater capacity means that I could add more strong base or more strong acid to that buffer and not affect its pH value. All right, so if I want to be able to add a lot of acid or a lot of base, then I better have pretty large concentrations of HA and A minus. Adding acid is going to convert A minus into HA. Adding base is going to convert HA into A minus. Okay, so it's a reciprocal relationship. So the more that I have of those things in the solution, the greater the capacity is going to be for the buffer. It turns out for most, at least industrial and medical uses, it doesn't need to be very high concentrations because you're not adding huge amounts of a strong acid or a strong base. Okay, but this is in essence what changes the buffer capacity. Now, one way you can think of this is imagine that you have a glass of water and you add a few drops of purple dye. Okay, if you do that, you're likely to be able to see a color change in your glass of water. Okay, the capacity for color change in your glass of water isn't very great. So adding, several drops of purple dye is still gonna change the color. But now suppose you filled your bathtub with water and you add those same couple of drops of purple dye and you stir it around. Are you going to be able to detect the color change in your big bathtub? Probably not. Okay, the big bathtub has a large capacity, at least for resisting color change, so it's like a high capacity buffer. The more material that you have in the buffer, the more it resists changes to its pH, and more it resists changes to its basicity and its acidity. So let's summarize what we know about buffer solutions. They resist change to pH. When you add a strong acid or a strong base to a buffered solution, it will not change its pH by a very great amount. Buffer solutions ideally have roughly equal amounts of weak acid and conjugate base. And I would say, generally speaking, they become less effective when you have as much as twice as much of one versus the other. They still will work, but I take that back. Probably 10 times as much is an effective limit. All right, if you have more than 10 times as much of one relative to the other, it's probably not going to be a good buffer. They can be tuned to a specific pH, okay, and that involves selecting a weak acid that has a pKa near the desired pH value, and then tuning the concentration ratio so that you get to the exact pH that you want. Buffer solutions have a finite capacity for maintaining pH, so be aware of that and know that once you exceed some capacity, the pH will begin to change when you start adding strong acid or strong base to your buffer. And I mentioned during the course of the lesson, the blood is an important example of a buffer solution that helps you maintain the right amount of acidity in your blood or basicity in your blood so that necessary chemical reactions take place rather than being thwarted, if you will, by the presence of an acid. So I hope you've learned what a buffer solution is and a little bit about how it regulates the pH of a solution. Thank you.